let's talk about a triangle. So let's create a triangle of length 4 on the bottom. Then we'll create a triangle of length 3 up on the top, or going up. And then we'll create a hypotenuse of whatever this is. But I think some of y'all know how to figure out what this is. Let's call this, let's give it the name R, because it'll be useful for later. But it's also known as the hypotenuse. But we know a formula for this. It's 3 squared plus 4 squared. So actually, we'll go this way. R squared equals 3 squared plus 4 squared. And then that equals to 9 plus 16, which equals to 25. So then that means that R is equal to 5. All right, so the hypotenuse is 5. Well, okay, what about this? What's this angle? You know, I really don't know, but let's just measure it. Blender got some neat measuring tool that you can just use like this. And according to Blender, it says it's 37 degrees. All right, well, let's trust it. Let's go with it. This is a right angle triangle. Length 4, measuring from these points. And same with up top. That's how I started off. But let's create a little table now. But before we do that, we got to recognize some points. So given this angle of 37 degrees Celsius, Fahrenheit, 37 degrees of the angle, this bottom piece here is called the adjacent. And then this one here is called the opposite. And the one opposite of the right angle is called the hypotenuse. If the angle was here, this would be the adjacent, and then this side would be the hypotenuse. Sorry, the opposite. So it's always relative to which angle we're looking at. We could, they would flip. So let's create a little table here of, let's start with adjacent. And then let's go with the opposite next. And then add the hypotenuse. And create us a little table here. Now let me extend this to the right a bit more. Let me hide some of that so it's you can see more of the screen. Okay, let's create some columns for us to use. And the adjacent in our case is 4. And then the opposite is 3. The hypotenuse is 5. All right, so let's expand on this idea a little bit more to get an idea of some of these trigonometric values. Let's double this side here. We'll do it up top again, and then we'll go 3 up also. And then we'll also go another 3 up, so we'll go up to 6 up here. So then this side is equal to 5. The question is, why is this equal to 5? Because this is the same triangle. It's 4, 4. This is 3. This is 3. And then this is also 37. It's the same triangle as this one here because we went 4 this way and we went 3 up. Then we connected to that point, and it becomes 5. All right, so let's ask what's the adjacent of this one? Well, the adjacent is the length from here to here, which is 8. Add up those two bottom pieces. Add up the 3's together, you get 6. And you add up those, you get 10. Well, let's repeat it. Let's repeat this process. This time, we're going to go over, well, we'll go over 4 again. And this time we'll go up 8. Sorry, we'll go up 6. We'll go over 4 again. Then we'll go up 3, and then we'll come down here again. And we'll notice it's the same triangle we have. It's the 4. It's the 3 here. And this one's 6 though. And then this side's 4. It's another right triangle on top. And then this is 37 degrees. And notice that even this middle-sized triangle, it shared the same 37, and the big triangle is still sharing the 37 degrees. So here's another 5 length. But let me just draw out these little diagrams to get a less ambiguous representation. All right, so we got a whole bunch of right triangles. Okay, so now of this even bigger triangle, what's the adjacent? Well, it's these 3 4's put together. Oops, and that should be 12. And then the opposite is relative. Well, it's always relative to this one. Let's just make that clear. So that's how I came up with these ones too. Always relative to this. And then this one is 9, so that's the opposite. And then it's 15. You put those 3 5's together. Okay. What I'm going to do next is kind of ask, what's the similarities between some of these different sized triangles? And the similarities are always going to be measured against the with respect to the angle, this angle. So there's a relationship of all these values relative to the 37 degrees. Well, all the side lengths have a relationship, and let's just show you that it's let's just analyze the adjacent over the hypotenuse, the opposite over the hypotenuse, the opposite over the adjacent, the hypotenuse over the adjacent, the hypotenuse over the opposite, and then we'll flip this one and it's adjacent over the opposite. Yeah, okay, I think that's right. Okay, let's look at the adjacent over the hypotenuse. So that's this row, 4 divided by 5. All right, so 4 divided by 5. That's 0.8. 0.8. 8 divided by 10. So that's, yeah, because we're going for adjacent here. 8 divided by 10. Well, 0.8. All right, what do we got? We got 12 divided by 15. So this one's the adjacent, this one's the hypotenuse. That's 0.8 also. We'll just have to try it, confirm it using a calculator, because I can't do it in my head that easily. But yeah, I'm pretty just check it out. Pretty sure it's that. All right, so opposite over the hypotenuse. All right, so that's 3 over 5, right? All right, so 3 over 5, what's that? That's 0.6. 6 divided by 10. Another 0.6. Well, I'm pretty sure this is also 0.6, so I have to check that. Let's go with opposite over adjacent. So that's this one, 3 over 4. should be 0.75. And if you keep doing this, you'll notice that you'll get this 0.75 opposite over adjacent. So that's, 6 over 8. You'll divide that to get that. 9 over 12. 9 divided by 12, sorry. It should be 0.75. All right, what about hypotenuse divided by adjacent? Well, if you take the hypotenuse and divide it by the adjacent on this, that's 5 over 4. That should be 1.25. And if you repeat it for the other values, the 8 over the 10 over 8 and the 15 over 12, it should come out to 1.25. And then what do we have for hypotenuse over opposite? So that's this one over this one, which is 5 over 3, 10 over 6, and 15 over 9. All of those are 1.66 repeating, I'm pretty sure. I think. I don't know. Please correct me if I'm wrong. Hopefully that's right. All right, what about adjacent over opposite? So that's this, these ones on the left over this row here. So 4 over 3, that looks like 1.33 repeating. 8 over 6, it's still, these all look like 1.33 repeating, so I would plug that into a calculator just to double check. So it's something like that. So we get this tail, but I think the most important thing to realize is that for this angle, this is all for the angle of 37 degrees, this specific table. And it's, if you notice, and it's always specific to the right angle triangle. And if you notice, these values are always the same. 0.8s, 0.6s, 0.75s. You go along the columns and the ratios, they always are something like this. And this is the relationship between different sized triangles. And so what people did is they just said, all right, this is, they said, all right, so the cosine of 37 degrees equals 0.8. And then they said the sine, well, actually, no, you know what? No. I'm going a little bit ahead of myself. Not do that. What they did is they gave these ratios labels. They're like, okay, this one's the cosine. This one's the sine. This one's sine. This row is tangent. This one's secant. This one's the cosecant. This one is the tangent. No, sorry, the cotangent. And they're all defined, but just by using the ratio. And what kind of ends up happening is that you end up, this table is specific just to one angle, and and what we realize is you don't need to create a whole bunch of different triangles, since all these are always the same. Just choose one triangle size, and then you could find a relationship between the cosine of 37 degrees and its value. You end up with a 0.8. And what you do is what people did is they created another table of this. They have like the cosine table, and that we'll call this one a theta, the angle, and then they have the cosine of theta. And then what people did in these, well, actually, no, you know what? It doesn't have to be the cosine. This could be a little bit more generalized. That's not what I wanted to do. I wish I knew how to undo that, but that's fine. All right, so then what people did is they just, generalize this stuff. They're like, all right, let's try to figure this out for all these things. right, so we got sine 10. I think we got one more. They created these massive tables, and then they put sine here, and then they put 10, and then they put secant, and then they put cosecant, and they put the cotangent, and then they're like, all right, so we did this for 37 degrees. Oops. Got 37 degrees. And they're like, okay, what are the values for that? Well, here are the values. We have 0 0.8, 0 0.6, 0 0.75, 1.25, 1.6 repeating, 1.3 repeating. And I'm getting these all from this other table. And then what people would do is, okay, let's do this for another angle of 38 degrees. And then they go, all right, let's create another line. Figure this out. So then they would adjust the dimensions of they would create a right angle triangle. And then they would use a protractor, measure it out to 38 degrees. They'd measure out a 38-degree one. And then they do some measurements on this side, do some measurements on that side, and then they would get some more values for this, and they'd use these ratios, and they'd get some more values for all of these, and then they'd keep repeating this. And then you have yourself a nice little table. And then you can use this table to figure out angles if you know the sides or something like this. So this is, at least, this is what I imagine people did back in the day. I can't say for certain, but this is what I think how people would come up with tables of cosines and sines and all these cosecants and all this stuff. But I also want to point out some other details about this, about these functions. Notice that the cosine is related to the secant. They're inverses of each other. Like if you look at the adjacents on the bottom, the hypotenuse is on the top. These ones. And same thing with this here and this. And then this one and this one. They're all, sort of inverses of each other. Well, what exactly is that? It's like cosine of, like for example, if you do that adjacent over the hypotenuse, if you use that reciprocal rule, it's hypotenuse over the adjacent. So they're sort of like in reciprocals of each other. And this one here, this adjacent on the left side, well, what is this? This is the cosine. This is the cosine of the angle. All right, well then what about this one? This one is, what is that? Hypotenuse. This one's the secant. And so you can create these relationships of these trig functions. But it's probably better if it was done the opposite direction. Because it's well, actually for the triangle, I think it's fine. For the triangle, it's okay. This one's cotangent. So yeah, that's kind of what we get out of this. And I guess what you could do for right angle triangles. Yeah, this is all for, just right angle triangles. So that's kind of like what people were doing to create all these trig functions. So this is all just right angle triangles. Well, the problem with right angle triangles is that you can't really have triangles with another right angle in them. So what would happen? It would look kind of like this. You would have this right angle here, you have another right angle, but none of this can form an actual triangle. It's always going to be something weird. And because of that, you could have one line that's this high, and because the if you could have a line that that is that high with all these other dimensions the same, the you could have another one that's that high, or you could have one that's really small. But whatever angle here is, if you try create these tables, they're going to be of all different like values, and you're never going to have anything that's like the same. So you can't. And then what happens with this table is that it's never possible to create anything that's consistent. And it's the same thing with this. If you have the angle that's bigger than 90 degrees, you can't really have this triangle. So yeah, the lengths get all messed up. You have a length that's bigger, a length that's smaller. And then there's the other issue of, well, what about if the angle is 0 degrees? What does that mean to have a 0 degree triangle? Well, you'll have one. So as you get the angle smaller and smaller and smaller, it degenerates to just a line. And with the line, you have like almost zero height. And if you have something with zero height and you try to divide it by, well, in this case, 0 would be the opposite because the angle's on this side, then these these columns are undefined. And it might make sense for the other columns, but yeah, since these columns are undefined, it's a little odd. Okay, so that's for right angle triangles. So that means that this table here, when you're trying to calculate what it could go up to, it's gonna go like really close to like 89.9 degrees or something. They'll probably have it up to with right angle triangles. And then the smallest you can get it is to like 0.1 degree or something, depending on how awesome your protractor is. All right, so let's go on the coordinate. Let's go with the coordinate definition, like coordinate sort of definitions. This might not be the technical term because I know people like to, say it's the unit circle, I think. But I think it's good enough just to understand what's really happening. So let's create sort of a y-axis. And then the x-axis. And then let's say we'll create our same triangle with the, there's 4 here. And then we'll go up to 3. So this will be 4. And then this one will be, at 3. So you're given a point in space for 3. It has a distance. Let's call this distance the radius. So the r radius. We know what r is in this case. It's 5. Why is it 5? Because this is the same triangle we had over here. It went 4 this way and then 3 up. We look at it, we have, again, 4 to the right and then 3 up. And it's 37 degrees. But what I want to do is I want to show you that this definition of the cosine, let's say, is going to be a little bit different. We want to, what we did before is when we said the cosine of 37 degrees, we said it was equal to the adjacent over the hypotenuse. In this sense, we kind of do have the hypotenuse right here at 5, but we're going to call it the radius instead. And then we do have the adjacent. In this specific example, it's 4. It's this one right here. But it breaks apart when it comes over to this other side. So let's create another one. So we have 4, -4, sorry. And then we have 3 this way. So this one's -4 and 3. Well, since it's a mirrored version, this is also 5. Since it's a mirrored version of this triangle, just the opposite side, this is 37. The cosine of this one, well, actually, there's an angle here, which we'll show later. But actually, you know what? Let's figure out the cosine of this. So we know this is a 90-degree angle right here. 90 degrees, right? Right there. So what is, well, actually, no. What's the easiest way to do this? Okay, I think I know the easiest way to do this. What we need to figure out is this angle here, this really big angle. I'm gonna get rid of that. This huge angle right here. This is the angle we want to figure. This is the angle we want for this cosine. It's not this one, because this one still gets into the idea of using a triangle. This time we're gonna abandon the triangle. Even though there's a right angle here, we're going to abandon the idea of a triangle and just go with coordinates and the distance to the center, the radius. The angle of this thing is what exactly? Well, we know it has to, since it's along a straight line, we know that something plus we know that something plus 37 is equal to 180 degrees, because this line has to be 180 degrees. So, all right, so what's that something plus? So something here, we got to put something here that adds up to 180 degrees. And I believe it's, well, the better way to do that is to just say, we could just guess it. There's different ways to do this, but I just want to put it in this form. I think it's the 3 will add up to this. So you put a 1 here. So 4 plus something comes to 180. Let's say that's 143. 143 degrees. All right. So I think this big angle is 143 degrees. 143. Yeah. Okay, so then to ask the question, to go back to the cosine of 143 degrees, we're trying to get out of this definition of saying adjacent over the hypotenuse. Because what is the adjacent? It might be tempting to say that this is the adjacent, but it's adjacent to 37 in this triangle, but we're really asking for 143. And there's really, it's odd. It's hard to get this right. So we still want to use this value here. And it's still going to be this value along the x-axis. So we'll just say cosine is related to the values along the x-axis. So what we'll do instead is we'll just say, all right, we'll just choose this one. And we'll just choose this x coordinate. So we'll abandon the idea of adjacent. And then we'll put it over -4, which is that x coordinate. And we'll go over to the length, the distance, the radius over 5. And then same thing over here. No more adjacent. It'll all be the x coordinate over the length of 5. So then the cosine of 143 is equal to the negative value of 0.8. And then this one's equal to 0.8. And it kind of makes sense since they're kind of the mirrored versions of this coordinate across the y-axis, but the angle isn't really mirrored. The angle is 143. It's the big angle. So if we use this definition, then we could use it for any coordinate point in this x-axis, y-axis plane. So for example, if we chose something random here, the distance to it, we can measure it out and we'll find it to be some value. Well, let's just call that value r for now. And then it has an x, it has a y value, a y coordinate, and the x coordinate is here. And its y coordinate is right here somewhere. But what's its angle? Where does its angle come from? Well, let's erase some of this stuff to make it a little easier to see the angle. All right, I think that's okay. I'll recreate the distance for r, and then this. The angle is always going to be measured from this x-axis to the right. It's always going to be something like this. So that's the angle. Let's call this angle theta. Maybe something like this. We'll call it some angle theta. And so in terms of this definition of cosine, now we're going to have the cosine, actually maybe I'll just go over here, the cosine of theta of this angle is you always choose the x coordinate and then you divide it by the radius, the distance to that coordinate point here. And so then it's x divided by r. And then we can do this for the other ones in a similar fashion. We get away from the opposite hypotenuse stuff. We'll just use the coordinate value, x over or y over r, and then the tangent is equal to, I think it's the opposite. Well, yeah. Well, if we want to go consistent, it would be opposite. Kind of, the opposite over the adjacent again, but we'll just use direct coordinates instead. And then we could also have the secant of theta equaling to sort of this ratio inverse. And then the cosecant, same thing, this ratio, put that sort of the radius on top. And then the cotangent is then this ratio inversed. That's kind of the more general version of the definition for these values. And I think it's important to include the radius and say that it's for any point, because you could analyze just along the unit circle, but I think this allows for a more similar definition to like how we're just doing this. And we avoid unit circle for now. And that maybe unit circles something we can do later. But I think this is uh, personally I like this coordinate definition. There's probably a different word for this, so don't rely too heavily on that. But we can see that these are kind of related. The cosines are sort of related to the secant. But let me just make some notes about the secant. In that, if x is 0, so like if you put a coordinate along this thing here, along the y-axis, where x is 0, this secant is really not, doesn't make much sense. If r is 0, that means that the radius, that means the point has to be exactly on the origin. And in that case, the angle doesn't make any sense. So cosine, sine, secant, cosecant, where if y was 0 along the x-axis, they would all be undefined. Similarly for these ones. But what I think is really interesting is that even though x and y might be 0, these functions still are okay as long as the r isn't 0. They still have values. So I think that's why these are chosen a lot, because they still like are defined when x and y are like intersecting with the, you know, the x-axis, the y-axis, when those values are become 0, and they don't degenerate into undefined values like these ones do. Which isn't really the case for the right angle triangle definitions, because as long as you have a legit triangle, a right angle triangle, like a lot of this stuff isn't going to be 0 and you don't have to worry about it. And they have a nice equivalency where pretty much all the values are defined over, whereas this stuff doesn't really. But what you'll notice is that the triangle, this one, is just a special case of the coordinate definition. Specifically, this would be the where the x and the y come into play in the coordinate space, and maybe this is the origin. And then this is where your x comes from, and then it connects to a y over here. So it's a special case of the coordinate definition, and that's how those two are connected. But the coordinate definition says, okay, I'm not gonna care about what the adjacent is. I'm not gonna care about what the opposite value is. I'm just gonna care about the distance to the origin from its current location, and that we'll call that the radius. And then it's gonna say, once I drop what adjacent means and opposite means and hypotenuse means, it just says, okay, now we can handle angles that are greater than 90 or equal to 90, or pretty much any angle from negative infinity to positive infinity, excluding those endpoints. And then you get this nice simple and easy to understand definition of what cosine, sine, and tangent are, and how they can be expanded to handle larger values of the angle. And yeah, I guess that's mainly it, the larger values of the angle of theta, because that was the issue with this, with right angle triangles. And then this table wouldn't no longer end here. In this example, once you start using x over r, you could start getting, you know, in y over r, you could start using like theta to be this now. You could start creating a table with the columns of everything here, and then you could start getting some interesting data for that, and you know, yeah, and you get everything you need. Uh, okay, yeah, I think that's good enough for now. Appreciate if you made it this far. Thanks for watching, and I'll try to come out with more stuff. Maybe it'll be something that's specifically noted that maybe I'll try to expand upon. But hopefully this made sense, or hopefully I explained it correctly. But yeah, have a good day.